Hi. There's a fairly common motion problem type that gets presented to students on the AP test I'd like to address. It's called oil drop diagrams, or sometimes called spark timer diagrams or ticker tape diagrams. Let's just explain what that is. So, the idea with these, we'll just call them oil dot diagrams, is that I have a mark that is placed at consistent time intervals. So the reason we call it oil drop diagrams is imagine there's a car and oil drips out of it like once every, say, half second, or once every second, or once every 2 seconds. Now, I gotta say, as a person who teaches AP environmental science, I don't really like these examples. Oil on the road is not a good thing. But anyway, it's a pretty standard convention. Now, sometimes we can use ticker tape. So I have like a piece of tape that's basically being pulled through this machine that will like put little holes or sparks or burn marks in it, again, at very fixed time intervals. So what varies is not the time. What varies is the delta x between the points. So the assumption is that we'll always have a fixed time between each of the marks, but what can vary is the distance between them. Now, we need to be told which mark is the first one to pay attention to, t equals 0, and which one is the final. Well, we don't have to be told which is the final. We just need to know which one is the first one, and we can figure it out from there. So, first thing we can tell, probably most important, is let's look at the distance between them. If the distance between each of these marks is always the same, then clearly it's not accelerating. It's covering the same delta x in every delta t. So therefore, it has no change in velocity, so no change in those two variables. So let's just look at the case here. So if I'm told that the distance between these marks here is 3 meters, then I'd say, okay, well, delta x is 3 meters, and delta t is zero point 0.5 meters, because these are deposited every 0.5 meters, 0.5 seconds. So therefore, I can say 3 meters divided by 0.5 seconds gives me 6 meters per second, and I know it's traveling to the right because this is t0. So therefore, time over time is traveling to the right. Now, what else can we tell? Well, if I look at these dots are not consistent distance apart. Now, I know this one is t0. So that doesn't mean it is started at rest. It just means that this is the first drop I'm paying attention to. And what I see here, without knowing anything about the time interval between the dots, without knowing anything about the distance between the dots, don't even need to know that, I can look at this and tell you this is not traveling at constant velocity. In fact, I know that it is slowing down, because although I don't know what the delta t is between these dots, I know it's always the same. And I know that in a given time interval, the object is traveling to the right a smaller and smaller distance, which means it's slowing down in the right direction, which means it's undergoing uh, a negative acceleration. It's slowing down as it travels in the positive direction, which makes it a negative acceleration. Similarly, if I was told that this dot was t0, then I go, well, as time goes by, it's traveling a greater and greater and greater distance in equal time intervals as it moves to the left. So since it's going, this is a faster velocity than this, which is a faster velocity than this. So I know it's gaining speed as it travels in the negative direction. So therefore, it has a negative acceleration. Now, if I look at this, this is t0. So I see in the first time interval, it covered this distance. In the same time interval, in the next time interval, in the same amount of time, the same delta t, it traveled a smaller delta x, and a smaller delta x, and a smaller delta x. Now, delta x is negative, it's moving in the negative direction, but it's moving less and less in the negative direction each time, which means it's moving slower and slower in the negative direction. So it's got a negative velocity, a negative direction to its motion, but it has a positive acceleration. It's slowing down in the negative direction, which is what happens when you have a positive acceleration. Often they'll present you with things like this, where the motion changed at some point during the time intervals in which the dots are being deposited. So if I'm told this is t0, and I'm giving the distance here, then what I see is the object had a positive acceleration. It was speeding up in the positive direction. And now look, at this point here, the distances between them are always the same. So between 25 meters and 75 meters, there was no change in how far the object went each time interval. So therefore, it was traveling at constant velocity. And now I see the dots get closer together, meaning that it is still traveling in the positive direction, but it's going more slowly. So what I see then is I have a positive acceleration. I'm going faster in the positive direction. Then I have a constant positive velocity. I'm traveling in the positive direction at a constant rate. Now I have a negative acceleration. I'm moving positive. Its velocity is still positive, but its magnitude is getting smaller. So therefore, it's undergoing a negative acceleration. Now, if I was asked, as I would often be asked, to calculate either the accelerations or the velocity, in this case, let's just say I'm asked to say, well, how fast was the car traveling when it was traveling at a constant velocity? I would look at the dots and I try to find where they have a consistent distance between them. So I can see that uh, from 25 to 75 was that's 50 meters, and it took it 1, 2, 3, 4 seconds. I know because I was told the dots are 1 seconds apart. So this is T0, 1, 2, 3, 4. Wait, Mr. Simpson, I thought this was T0. Why do you call this T0? I get to choose to call whatever I want to be T0. I'm just looking at the change, right? So how much time, but don't call this one 1. That's a mistake kids make. If I start here, that's 0. 1 second later, 2 seconds, 3 seconds. It took 4 seconds to get from here to here. So that is 75 minus 25. That's 50 meters. It took 4 seconds. Therefore, it's traveling at 12.5 meters per second. But I know that at time equals 1, 2, 3, 4, 5, 6, 7, 8, it began to slow down and have a negative acceleration. Okay, let's try another one. What if I was asked to find the acceleration of this one? Okay, I know it's accelerating because the distances between the drops are getting farther apart. I'm told that they're deposited a rate of 1 drop per second. So if I was asked to find the car's acceleration, I have two different approaches. Let's start with approach A. With approach A, what I could say is, all right, I can say that look at any moment in time, the velocity is never the same. At no point between here and here was the velocity ever the same. It's accelerating. So one strategy is say, well, I'm going to take the average velocity here and the average velocity here. This is like what we do with photo gates. And say, I'm going to find the average velocity here and call it VI. I'm going to find the average velocity here and call it VF. Even though between here and here, the velocity changed, between here and here changed. I'm going to find the averages. Then I'm going to use this equation here to solve for acceleration. But I've got to be a little bit careful what I choose for delta t here. So if I say, well, it went 1 meter in 1 second, so its average velocity in this interval was 1 meter per second. And here it traveled 1, 2, 3, 4, 5 meters in 1 second. So it's going 5 meters per second on average between here and here. Right? It started off at one thing, which wasn't 5. It ended at something that wasn't 5, but its average was 5 in this time interval, right? So what do? Now, I can use these values here, but I have to be careful what I choose for time. So I'm going to say the final was 5 meters per second on average. The initial was 1 meter per second on average. And then what I'm going to say is I'm going to make my T final is going to be halfway between here and here. So this is 1 second, 2 seconds, 3 seconds. So what's halfway between 2 and 3 seconds? 2.5 seconds is. I'm going to call the middle point here. And what's the middle point between 0 and 1 second? Was 0.5. So I'm going to call my T initial, I'm going to call it 0.5, not 0. If I do that, what I see is I come up with 2 meters per second squared, which is how fast this object was accelerating. Mr. Sampson, this part here drives me crazy. I get it. It's something we need to practice. Now, there is another way of doing it. Let's try another way. So strategy B would be I'm going to take the V average for the entire duration, and I'm going to use this equation. I'm going to say, well, since I know it started from rest, I was told that, then I can use this one here where I can say, well, then the average is V final plus V initial divided by 2 will give me the V final, and then I can use it. Let's just try that. So if I do that, I'm going to say the V average it went a total of 9 meters. It took a total of here's T equals 0, 1, 2. It took 3 seconds. So the average velocity all the way across here is 3 meters per second. Now, average velocity is equal to V final plus V initial divided by 2. That's why it's an average of 2 points. And I know this one was 0 because it started at rest. So if I do that, what I find is the if I solve this for v final, I'll come up with it was actually going 6 meters per second. Remember in the last one we said the average speed across this distance here was 5, but here it's actually 6. So now I know what the actual final velocity is here. I can then use this equation here and say, well, 6 meters per second minus 0 over 3 seconds gives me 2 meters per second squared. All right, guys, let's start practicing these. See you tomorrow.